Welcome to a geological journey across the top of Australia. This journey is in memory of an extraordinary Australian, Malcolm Douglas. Malcolm was the analog equivalent of the YouTube digital platform. Many of his adventures across the top of Australia are presented on YouTube. The viewer of this presentation will have noted by now that the Jack Hills location is indicated on many of the background slides. This has been done for two reasons. The first is that the author has extensive knowledge of the Jack Hills, having spent many months there mapping the entire length of the Jack Hills range. The second is that the Jack Hills have zircons that are some of the oldest ever discovered on the face of the Earth. Detrital zircons with ages greater than 4,000 million years ago have been found in the siliciclastic rocks, interpreted as alluvial fan delta deposits. The oldest is a 4,404 million year ago zircon found at the Oranondo Hill by Wilda in 2001. This is the oldest dated material found on the Earth. Here you can see catholuminescent images of the 5 zircons, which have been age determined and are the oldest zircons ever discovered on Earth. So in our journey across the top, we will be looking at researching some of the oldest rocks that were created near the origin of the Earth itself. The islands, nation, continent, Australia. Across the top. And the same area across the top of Australia as presented by Karen Connors 2023 in her presentation Crustal Architecture and Evolution of the North Australia Craton. The Pilbara Craton. Kimberley Craton. Pine Creek Craton. Arnhem Craton. So the cratons recognized and proposed by Connors 2023 are Pilbara, Kimberley, Pine Creek, and Arnhem. The Pilbara Craton. Geological mapping of the Pilbara Craton has been more detailed and more comprehensive because of the proximity of the Hammersley iron deposits, which are some of the biggest, the giants of the world. It is both interesting and instructive to compare the Zimbabwe Craton in southern Africa with the Pilbara Craton of northern Australia. Laux and Campbell, 1998, recognized what they labeled as fossil cell arrays in the Zimbabwe Craton. Note that the granitoid gneisses and plutons presented in the Zimbabwe Craton are comparable in size to those seen in the Pilbara Craton. That is, they are generally 50 to 100 kilometers in diameter. It is likely that the granitoid gneissic plutons presented here are equivalent to the sodic granites of the tonalite trondhjemite granodiorite TTG series presented by Johnson et al. Johnson et al. 2022, in their paper titled Giant Impacts and the Origin and Evolution of Continents, show that the Pilbara Craton was created through a giant meteor impact. They show that the oldest preserved continental crust mostly comprises sodic granites of the tonalite trondhjemite granodiorite, that is the TTG series. This series is derived over time through partial melting of hydrated basaltic rocks, that is, amphibolites, at depths of around 25 to 50 kilometers. We will be using this model as presented by Johnson et al. As an analog for the other cratons discussed in this presentation. Johnson et al., using the oxygen isotope compositions of dated magmatic zircon, showed that the Pilbara Craton is the Earth's best preserved Archean 4 to 2.5 billion year old continental remnant. It was built in 3 stages. They go on to show that the shallow melting present at the Pilbara Craton is consistent with giant impacts that typified the first billion years of Earth history. And note that giant impacts provide a mechanism for fracturing the crust and establishing prolonged hydrothermal alteration by interaction with the globally extensive ocean. Determining the anisotropy in the Earth's mantle is useful in respect to understanding the impact that meteors have had on the mantle in the past. Kirby, 2022, in his book titled Spectral Methods for the Estimation of the Effective Elastic Thickness of the Lithosphere, shows that mechanical anisotropy is critical in understanding the dynamics of the mantle. Quote, the effective elastic thickness, commonly known by its mathematical symbol Te, describes an important property of the lithosphere, namely its flexural rigidity or resistance to flexure by loading. But, besides describing this particular behavior of the Earth, Te has been shown to play a vital role in tectonic evolution, with zones of low Te deforming much more readily than regions with high elastic thickness, such as the ancient cratons that core the continents. We will be using mechanical anisotropy to analyze Australia's mantle. The model created by Kirby et al. Has been especially useful in understanding the mechanical anisotropy of the lithosphere in Australia. Quote, we develop a new method for imaging the spatial variations of the anisotropy of the flexural response of the lithosphere and apply it to recent topographic and gravity datasets over Australia. The method uses two-dimensional Morlet wavelet transforms superimposed in a strictly controlled geometry to estimate the auto and cross spectra of the two datasets in a number of different directions. The resulting wavelet coherence is a function of scale, or wavelength, as well as orientation, and is inverted at each spatial location. For the three parameters of an anisotropic thin plastic plate model, that is, maximum and minimum flexural rigidities and the orientation of the maximum. Extensive tests of the method on synthetic anisotropic but uniform datasets show that it retrieves the amplitude and orientation of the anisotropy with useful accuracy. The results for Australia west of 143 degrees east show a strong correlation with the shallower layers, that is 75 to 175 kilometers, of a recent model for seismic SV wave azimuthal anisotropy. The weak axes, that is the minimum flexural rigidity, in most cases are approximately at right angles to the fast axes of the seismic anisotropy, implying that for Precambrian Australia they arise from the same source. This is most likely deformation resulting from the most recent episode of orogeny. The following map of Australia shows the distribution of weak axes, that is, those with minimum flexural rigidity, delineating major geologic features such as the characteristic pattern over the Pilbara Craton and others. Note that the anisotropy has a uniform or slowly varying direction that changes more abruptly over the Pilbara Craton boundaries. Mechanical anisotropy and the Pilbara Craton. Another location showing an abrupt change in mechanical anisotropy. And that location coincides with the Kimberley Craton. This detail shows the diversion of the mechanical anisotropic vectors being diverted around the Kimberley Craton. And using the same criterion, another location is found where there is a rapid change in the direction of mechanical anisotropy. And this location coincides with the Pine Creek Craton. Another location showing an abrupt change in mechanical anisotropy, which coincides with the Arnhem Craton. One can see that the cratons are delineated precisely by mechanical anisotropy across the top of Australia. Another location showing an abrupt change in mechanical anisotropy. I have labeled this the York Craton. Another location showing an abrupt change in mechanical anisotropy. The Brisbane Craton, or is it an impact? The Sydney impact. The Tasmania impact. The Cape Leeuwin impact. Noting, as mentioned previously, the proposed meteor impact by Johnson et al. 2022 of the Pilbara Craton. And finally, the proposed Deniliquin meteor impact by Glickson, 2022. Musings. It is noted that all of these circular features are of similar size, that is, they have a diameter of 500 to 700 kilometers. If all of these are ancient cratons, that is, originated as meteor impacts, both the similarity in diameter and the geometrical arrangement, that is, along the edge of the continent, seems unlikely. One would expect a much more random size and random spatial distribution. Is it possible that we're seeing an artifact, that is, an edge effect, created by the chosen window size of the Morlet-Wavelet transform? Yet there is no edge effect where these circular features across the top of Australia coincide exactly with known cratons. Let's investigate further into the possibility that we have created an edge effect. This is an example of a Morlet-Wavelet transform at different window sizes. At the top is a scale of 1, same number of oscillations, but now stretched out into a window that is scale 5, and the bottom one being scale 10, with the same number of oscillations. So the red arrows indicate the window width of our wavelet transform. Using the various window sizes, Kirby and Swain have analyzed the topographic and gravity data for all of Australia. Both Macario et al. 1995 and Swain and Kirby 2006 have looked at the possibility of creating artifacts when using wavelet transforms to analyze topographic and gravity data. Swain and Kirby note that when the window is not much larger than the flexural wavelength, the effective elastic thickness, that is TE, can be overestimated. They note that there may be some edge effect due to the proximity of the cratons to the coast, causing a downward bias in our wavelet TE estimates. But this is speculative, as we, that is Swain and Kirby, have not been able to simulate it with their synthetic models. Thus, they concluded that since they were unable to create an edge effect in their synthetic model, the circular features along the edge of the Australian continent are real. So the question is, since we've accepted these circular features as significant and real, what exactly do they mean? Especially in respect to continents and tectonic plates. The land area and continental shelf of Australia. Note that most of the circular features fall within the continent of Australia itself or on the continental shelf. Two exceptions are the Brisbane and the Sydney circular features. For these two features, more than 3/4 of each is beyond the edge of the continental shelf, which begs the question, where is the other 3/4 of each of these circular features? It will be shown in the next part of this presentation that the Australian plate has spent the last 50 million years migrating northward from its connection to Antarctica. It is possible that the eastern three-quarters of each of these circular features have been faulted and left behind during the migration. It has become obvious that what was initially across the top of Australia, relating mechanical and isotropic features to various cratons, has ultimately included the entire continent of Australia. This has led to the necessity to look at across the middle of Australia so we can evaluate its geological tectonic core. What are cratons? An excellent summary is provided by Groves and Santosh 2024 in their book Mineral Systems, Earth Evolution, and Global Metallogeny. They note subcircular Precambrian cratons, normally in the order of 1,000 kilometer diameter, are the foundation blocks of all continents on Earth. They represent the older and most stable components of the continental lithosphere that occupy the central portions of tectonic plates. A Bouguer gravity anomaly map for all of Australia. Here I have delineated some of the more obvious features. Note especially the flattened oblate Musgrave province feature, which is located near the very center of the Australian tectonic plate. All of the other easily recognized features are circular. It is proposed that the Musgrave feature was originally circular and the site of a major meteor impact. Evidence for the flattening, the oblateness of this originally circular feature follows. This is the location of the proposed Musgrave meteor impact on our mechanical anisotropy map of Australia. The possibility of multiple circular features within the Australian continent is not new. Here we can see proposed circular features by O'Driscoll and Campbell almost 30 years ago, and how those circular features are related to mineral deposits. However, the real problem in accepting these circular features is that, for the most part, they are open to interpretation and are not based on factual evidence. By superimposing the two data sets, it is obvious that many of the features interpreted to be present by Campbell and O'Driscoll are also present on our current mechanical anisotropy interpretations for Australia. Earlier in this presentation, the movement of the Australian plate northward was alluded to. That tectonic movement is supported by using current GPS measurements. Using current GPS measurements, one can see that Australia's movement northward is quite extreme compared to GPS measurements in other parts of the world. Observing Australia in isolation, it becomes obvious that the central part of Australia is moving northward at twice the rate of the rest of Australia. This more rapid movement for the central part of Australia has not only flattened the Musgrave Range province, but has also created the Great Australian Bight. Makes one wonder whether that is B-I-G-H-T, Bight, or B-I-T-E, Bight. Quote, the Great Australian Bight came into existence about 50 million years ago, when the supercontinent Gondwana broke apart, separating Antarctica from Australia. We will be utilizing magnetic anomalism of the Australian plate to help understand processes within the lithosphere, the upper mantle. However, before diving into magnetic data, please recall, in respect to mechanical anisotropy, that Te has been shown to play a vital role in tectonic evolution, with zones of low Te deforming much more readily than regions with high elastic thickness, such as the ancient cratons that core the continents. Those regions that are much more readily deformed are especially revealed through magnetic data. A total magnetic intensity anomaly map for all of Australia. Again, I have delineated some of the more obvious features. The oblate characteristic of the Musgrave Range feature is well represented here in magnetic data. As shown above, the northern migration of Australia has caused compression, especially in the central part of the Australian continent. The relative migration rates for the central part of Australia compared to the eastern or western edges has caused flow. These are represented by flow vectors in the following movie. With this differential in migration of the edges of the continent versus the center would cause flow vectors where east of the Musgrave province, the vectors would be to the east, and west of the Musgrave province, the vectors would flow to the west. The scientific models created up to this point in this presentation are important. These models present quite a different view of the patterning and the geometry of the Australian continent. However, the most important takeaway from this presentation is how these models relate to world-class ore deposits. And that takeaway is why knowing the locations of cratons, that is, ancient meteor impacts, is important. As McQuaig and Wronski in 2014 state, giant ore deposits are zones of focused mass and energy flux. They go on to state that giant mineral deposits have an association with large, long-lived, deeply penetrating, and steeply dipping structures that commonly juxtapose distinctly different basement domains. These structures are vertically accretive in nature, often having limited or subtle expression at or above the level of ore deposition. Quegg and Wronski's conclusions are very much in line with those of Billingsley and Locke almost 60 years ago. In their structural analysis of the ore districts of the United States in a continental context, they concluded that giant deposits occur where there are superimposed deformations of different ages which strengthen the rocks, making them competent to carry channels to depth. They go on to say that these deep penetrating breaks permit the passage of heat and associated products such as magmas, metamorphism, alteration, and mineralization from depth to the surface. The reactivation of pre-existing structures is a major theme for many hydrothermal mineral deposits. And it is being recognized more and more by geologists that the global distribution of world-class deposits occur on the edge of cratons. Here, Hogard et al. 2020 shows that the global distribution of sediment-hosted metal deposits is controlled by the edge of a craton. And those edges of cratons are the location of deep faults, which is also the edge of an ancient meteor impact. And even more recently, Groves and Santosh 2024 have recognized the genetic relationship of cratons and thick lithosphere margins in respect to world-class metal deposits. And what is required for success in mineral exploration, according to Nicholas T. Arnott et al. 2017, is discovery thinking. Quote, people are the key to discovery, and while teamwork is important, inevitably it is the individual flash of genius that sparks discovery. Discovery is not a consensus outcome. Someone has to lead the way, according to Dan Wood, 2010. It seems that inspired judgment by certain experienced geologists, rather than statistically derived prediction, is the key to discovering an ore body. Discovery requires intuitive leaps of imagination resulting from the human brain's ability to engage in lateral thinking, often by making decisions that deliberately ignore some information and then being bold in acting on those decisions. And finally, in discovery thinking, quote, the ability to make discoveries also benefits from the fact that humans are programmed to learn and be selective. And the old adage that the best geologist is the one who has seen the most rocks has truth to it. However, Nicholas Arnott et al. 2017 say, quote, geology is but one of several risks that need to be considered when deciding where to explore. And basing one's exploration effort purely on geology, that is, rock type, may constitute the biggest risk of all. And as a final tribute to Malcolm Douglas, here he is, a very game Australian, eating a witchetty grub in the outback of Australia.